Good morning to all of you. Let us start the lecture 3 of the wave optics. In the previous lecture, we discussed about the interference and the condition for the bright fringes and the dark fringes. So here we will discuss Young's double slit experiment and colors in the thin film. Young's double slit experiment. S is a source, single slit, double slit, screen. The light coming from the single source passes through the slit, then it passes through the double slit. So these are the two sources, and then finally it falls on the screen, and as a result we obtain the bright and dark bands on the screen. So S is the source, S1, S2 are the two sources made from a single source. The light from the two sources S1 and S2, they come and meet at point P. So let us think that P is a point on the screen at which the two wavefront coming from S1 and S2 are interfering, and as a result they are meeting at point P. So now our problem is to find the position of the point P, at which position the value will be bright fringe, and at which position the value or we obtain a dark fringe. So let P is at a distance y from the center point O. Now let small d is the distance between the two slits S1 and S2, and half of it is d by 2, and capital D is the distance of the screen from the two sources. So let us listen again that S is a single source with the help of which we have made the two sources S1 and S2. From S1 and S2, two wavefronts starts, spherical wavefronts come out, and interference takes place, or we can say interference is the superposition of the two waves coming from point S1 and S2. As a result, the redistribution of the energy takes place, and on the screen we obtain a pattern of dark and bright fringes. Now our problem is to find out the position of these dark and bright fringes. So for this, let us consider that P is any point on the screen which is at a distance y from the center of the screen. Now the waves from S1 and S2 reach the point P with some phase difference and hence path difference. So let this path difference is S2P minus S1P. Now using the mathematical relations, now S2P square minus S1P square. Now from this diagram, P, S, O, not O below the point O, that is O dash. Look again, this side, and this side. This is the triangle. In this triangle, S2P, using the Pythagoras theorem, hypotenuse square is equal to perpendicular square upon base square. So in this, base is capital D and hypotenuse is perpendicular is y plus d by 2. So we can say that S2P is d square plus y plus d by 2 whole square, because we know that h square is equal to p square plus b square. Here h is S2P, to S2P square is equal to perpendicular square, that is y plus d by 2 whole square, and base is capital D, so capital D square. So we can say that in place of S2P square we can write this expression, and in place of S1P square we can write this relation, d square plus y minus d by 2 whole square. Now again, using another formula, that is a square minus b square is equal to a plus b into a minus b, and when you square, open the brackets, some of the terms will cancel out each other and we will get the result 2yt. So S2P minus S1P into S2P plus S1P is equal to 2YD. Now from here we can say that 2D is equal to 2YD. How? Because S2P and S2P minus S1P. Now since these are very close to each other, so S2P minus S1P or S2P plus this S2P minus S1P will be very little value, we can neglect it. S2P can be taken equal to capital D, so S2P plus S1P can be written as 2D, and difference between S2P minus S1P can be neglected because S2P is approximately equal to S2P. So here we have taken an approximation that S2P is approximately equal to S1P and it is approximately equal to capital D. So from here this approximation is very little value, so we can neglect it, and S2P plus S1P will give you the 2D. So this approximation we have taken here. So here this expression reduces to path difference or the del 2D is equal to 2YD. So del or the path difference is equal to YD upon D. So we can say that path difference is equal to YD into D. Or let us repeat it again. Now since S2P minus S1P is the path difference, so in that place we have written del, and S2P is approximately S1P, so that is 2D. So we can say that path difference is equal to YD upon D. Now with the help of this, now what is this? This is the path difference, that is S2P minus S1P is the path difference. Now with the help of this we will find the position of P. Now in the previous lecture I told you about the position of the bright fringes and the dark fringes in terms of the path difference. So using that, if the path difference is equal to the position of the bright fringes, then P will be the bright fringe, and if the path difference is equal to the position of the dark fringes is equal to the path difference of the dark fringes, then P will be the position of the dark fringe. So using this, now let us discuss the position of the bright fringe. For a bright fringe at P1, this path difference should be equal to n lambda, which we discussed in the previous lecture, where n is equal to 0, 1, 2, 3. So from here y is equal to nd lambda upon d. Y is the position of the bright fringe. So first bright fringe will be obtained at y0 is equal to 0, that is at the center point. Then n is equal to 1, y1 is equal to d lambda upon d, that is the first bright fringe, central bright fringe, then first bright fringe. For n is equal to 2 is the second bright fringe. For n is equal to n, that is the nth bright fringe. Similarly, for the position of the dark fringes, this path difference should be equal to 2n plus 1 lambda by 2, and from here value of y is equal to 2n plus 1 d lambda upon 2t. So from here, for n is equal to 0, the position of the first dark fringe, that is d lambda upon 2d. For n is equal to 1, 3d lambda upon 2d. For n is equal to 2, 5d lambda upon 2d. For n is equal to n, 2 plus 1 d lambda upon 2d. Now with the help of this we can find out the expression for the dark fringe. Now let us see that this is the position of the in the previous diagram, this is the position of P and Y. So position of the bright fringes. Now if y0 is the position of the center fringe, this is y1, or say y1, y2, y3 and so on, means this is the position of the bright fringe, y2 is position of the second bright fringe. If you find the difference between these two, because here you are getting bright, here you are getting bright. So in between you will get a dark. So expression for the dark fringe width. This will be the width of the dark fringe width, which is equal to y2 minus y1 or y3 minus y2 and so on. And in general we can say that this is the difference between yn plus 1 minus yn. So yn plus 1 minus yn will be the expression for the dark fringe width. Means by differentiate with the help of this difference we can find out the fringe width of a dark fringe. So beta is the symbol for the fringe width. So beta naught expression for the dark fringe width is equal to yn minus 1 or yn plus 1 minus yn. In both the cases you will get the same result. So yn is n d lambda upon d, and yn minus 1 means in place of n you will write n minus 1 d lambda upon d. When you simplify this you will get d lambda upon d. Similarly you can find out the expression for the bright fringe width, that is yn dash minus yn minus 1 dash, and when you simplify this you will put the value in this expression and simplify, you will get the same value, that is d lambda upon d. So from this and this is the expression for the dark fringe and this is expression for the bright fringe. So from these two relations we can say that all the fringes are of the same width, whether it is dark or whether it is bright. So the expression for the fringe width shows that the fringes are equally spaced on the screen. Distribution of intensity. Now here it is the position of the points on the screen, that is taken to be y, and on the y-axis we have taken the intensity. Suppose the two interfering waves have the same amplitude, say A, then the intensity, maximum intensity, in the previous lecture I told you maximum intensity is directly proportional to the square of the amplitude, and for the maximum intensity A1 plus A2 whole square. So from here we will get the intensity for the maximum value is proportional to 4A square, and all the bright fringes have the same intensity, and for minimum all the dark fringes have the zero intensity. So from here in these points they will show the intensity of the bright fringes, and these points will show the intensity of the dark fringes. Now condition for the sustained interference. Sustained means continuous interference. The two sources producing interference must be coherent. The condition for the coherent is discussed in the previous lecture. That is, the two sources should have having the same wave, same amplitude, same value of omega, and the constant phase difference. The two interfering wave trains must have the same plane of polarization. The two sources must be very close to each other, and the pattern must be observed at a larger distance to have sufficient width of the fringe. So from here the two sources must be close, means D should be very small. D is the distance between the two sources. If D is very small, then the fringe width, that is beta, is equal to d lambda upon d will be very large. And similarly capital D, that is the screen, should be very far away, so capital D will be large, then beta will be large. So for beta to be very large, capital D should be large and small d should be small. That is, we can say that two sources must be very close to each other and they should be observed at a larger distance to have the sufficient width of the fringe. The sources must be monochromatic, otherwise the fringes of the different colors will overlap. Now listen once again, that sources must be monochromatic. This is the condition for the coherent sources. Now if in place of single wavelength light we use a white light, यहाँ पर एक क्वेश्चन, ये आपका क्वेश्चन बन जाता है कि if in place of a single wavelength we use a white light, then what will be the effect on the pattern of the interference fringes? So in that case we will obtain the fringes of the different colors and they will overlap each other. The central fringe will be the white fringe, and after that we will obtain the different fringes of the different colors which are overlapping to each other. The two waves must be having the same amplitude for better contrast between bright and dark fringes, because if they have the same amplitude, then the intensity will be maximum at the bright fringes and minimum, that is 0, will be at the dark fringes. So they have the same amplitude for the better contrast between the bright and the dark fringes. Now color in thin films. Now let us consider that this is a very thin film. These are the two surfaces of a thin film. PQRS. Now the ray is incidenting on it from the surface PQ, it is reflecting. RS is another surface of the thin film from where it is again reflecting. I, angle of incidence. R, angle of refraction. T is the thickness of the film. So it can be proved that the path difference between the light partially reflected from PQ and that from the partially transmitted and then reflected from RS, means the path difference from the light partially reflected from PQ, this is the reflected from PQ, and then partially transmitted and then reflected from RS. So this path difference can be calculated, but that calculation is not in your syllabus. We can just simply discuss the formula that path difference between these two is equal to 2 mu t cos r. Since there is a reflection at point O, the ray OA suffers an additional phase difference of pi, and hence the corresponding path difference will be lambda by 2. Now this you have studied in class 11, that on reflection the path difference, the ray suffers a path difference of pi. There is a path difference, phase difference of pi on the reflection. So hence the corresponding path difference of lambda by hence the corresponding path difference, you know that path difference P is equal to that is lambda upon 2 pi is the phase difference into the phase, lambda upon 2 pi into phase. So when pi is to pi cancel out, so path difference is equal to lambda by 2. So when there is ray is reflected at point O, so OA suffers the additional path difference of lambda by 2. So the path difference for the rays OA and BC, they will interfere constructively. The path difference must be, for the constructive path difference we have discussed in the previous lecture that for constructive path difference for the bright fringes, the path difference should be equal to n lambda. But here the path difference must be equal to n plus lambda by 2. Lambda by 2 is the additional path difference, and this path difference should be equal to 2 mu t cos r. So 2 for the rays OA and BC to interfere constructively, that is the bright fringe, the path difference must be equal to n plus half lambda by 2. So 2 mu t cos r n plus half lambda by t. And for the ray OA and BC to interfere distinctively dark fringe, the path difference must be n lambda, that is 2 mu t cos r is equal to n lambda. So the bright fringes, the path difference must be n plus lambda by 2, and for the dark fringes the path difference must be equal to n lambda. When white light from the sun falls on a thin layer of a spread over water in the rainy season, beautiful rainbow colors are formed due to interference of light. Now these are the questions from your NCERT textbook based on the topic taught today. You just go through these questions. You may get the answer of these questions from your NCERT books, and if you have any doubt, you can discuss it any time. Thank you and have a nice day.